Normally I explain my theory since it is not part of the scientific conversation. That said, there is value in evaluating criticism. Due to lack of backbone and censorship, no cosmologists, astrophysicists, or even astronomers will take the other side of the discussion. This person claimed to be a cognitive scientist. It is clear the person is intelligent and made his best argument against my ideas. He prefaced his criticism with, "I am not a physicist, but I disagree with you and you are wrong." Smiley face. It is difficult to discuss with someone that protects themselves with a claim of ignorance. I don't know and I don't need to know to have an opinion. That said, I defended my position and highlighted his mistakes. Feel free to ask questions or to provide criticism. Criticism. There are other observations which allow us to conclude homogeneity as property of the universe besides inflation, which makes your claim sound rather strange. Answer: nobody is rejecting universe homogeneity. There are no observations that supports inflation. Inflation was created to explain universe homogeneity observed in the cosmic microwave background, and recent astronomical observations actually go against the homogeneity aspect. These observations are actually flawed because they focus only on luminous mass and not on the total mass, luminous mass plus gas. The Big Bang model does not predict the observed large-scale structures like voids and filaments. 1. Initial conditions and Gaussian fluctuations. The standard Big Bang model, combined with inflation theory, predicts that the initial density fluctuations in the early universe were nearly Gaussian and of small amplitude. These fluctuations are thought to have been seeded by quantum fluctuations during the inflationary period, which were then stretched to cosmic scales. The Gaussian nature implies that most fluctuations are small, with large fluctuations being exponentially rare. 2. Formation of large structures. The challenge arises when considering how these small, nearly Gaussian fluctuations could lead to the formation of the enormous structures we observe today, like superclusters, filaments, and voids. The growth of these structures is attributed to gravitational instability, where regions slightly denser than average attract more matter, growing over time. However, the scale of the observed structures seems too large to be easily reconciled with the initial Gaussian fluctuations. 3. Current cosmological models. The lambda cold dark matter, lambda CDM, model, which is the current standard model of cosmology, does account for the formation of large-scale structures. However, it relies heavily on the presence of dark matter to amplify the small initial fluctuations. Even with this amplification, the large voids and superclusters observed, like the Boots void and the Sloan Great Wall, present a challenge for the model. Some studies suggest that these structures are at the extreme tail of what the lambda CDM model predicts, while others argue that they might point to gaps in our understanding. 4. Non-Gaussianities and large structures. There is ongoing research into whether the initial fluctuations might have been slightly non-Gaussian or if other processes could contribute to the formation of large structures. Some researchers propose that the initial conditions may not have been perfectly Gaussian, allowing for more significant fluctuations that could seed the large structures observed. The hypergeometrical universe theory not only predicts the existence of large structures but also predicts their location and shape. Hence the first paragraph supporting Einstein and Guth is shot down. Criticism 0. I'm not sure why you appear to think that Nobel Prize is such an important factor in judging veracity or usefulness of one's discovery for all times. However, it was Nobel who made one of the requirements that his prize would be awarded only for the discoveries made in the previous year. When Guth wrote down his inflation formulas, it was decades before a number of observations were made which further validated his hypothesis, which is why Guth's contributions have been rewarded with a $1 million Kavli Prize and not the Nobel Prize. My explanation seems to fit the facts better than yours does, which makes me even more doubtful about your cosmology ideas. I mean, it's a lot simpler to become informed about the Nobel Prize than to study astrophysics. Answer: this is called swift boating someone else's work. You claim ignorance, not a cosmologist, which means you can always play dumb and feign not understanding basic physics, and then use a spurious argument to claim that my model is wrong. In your case, the spurious argument is, you don't know about Guth and Kavli Prize, so your theory is wrong. That is pure idiocy and a scurrilous behavior. Lame excuse: I'm no cosmologist, my background is cognitive, behavioral sciences, so I cannot evaluate your claims personally and directly. But there are things which are common to all of science, and since you clearly consider your hypothesis to be scientific, here are some questions about it. Ans, you premised your criticism with, I am not a physicist, but. The problem with that posture is that you are not in a position to evaluate anything that requires the simplest of physical reasonings. Critique 1. Question: how can your hypothesis be falsified? In other words, which future observations of the universe could, in principle, invalidate your hypothesis? Which recent observations appear to invalidate Guth's inflationary idea, for comparison's sake? Response: 1. Falsifiability of my hypothesis. My theory is a theory of everything, meaning that it is broad and covers all fundamental aspects of the physical universe, including gravity, electromagnetism, and nuclear physics. Because of its comprehensive nature, it can be falsified by any observation that contradicts the laws it predicts. For instance, any deviation in the behavior of gravitational forces, electromagnetic interactions, or nuclear processes from what my theory predicts would falsify it. Furthermore, my theory provides specific predictions about the density distribution of galaxies across the observable universe. These predictions can be directly tested with telescopic observations. If these observations do not match my predictions, it would falsify my theory. 2. Resonance frequency of the universe. My theory predicts the resonance frequency of the universe, which means that one can, in principle, listen to the universe. This is another observable prediction that, if contradicted by data, could falsify my model. 3. Inflaton particle and Guth's theory. Guth's inflationary theory hinges on the existence of the inflaton particle, which is supposed to carry the inflationary field. However, no such particle has ever been detected. Moreover, there has never been a measurement of the actual inflated size of the universe to confirm that it was indeed inflated and that it has boundaries somewhere far away. Essentially, there is no empirical support for Guth's theory beyond the cosmic microwave background, CMB, which inflation was invented to explain. If inflation were accurate, we would expect to find the inflaton particle or some other evidence supporting this mechanism, but none exists. It is up to Guth and proponents of inflation to provide this evidence. 4. Large-scale structures and the Big Bang model. The Big Bang model, which includes inflation, does not adequately explain the existence of large-scale structures like voids and filaments observed in the universe. According to the Standard Model, the initial density fluctuations in the early universe were nearly Gaussian and of small amplitude, seeded by quantum fluctuations during inflation. However, the scale of the large structures we observe today, such as superclusters and vast voids, presents a significant challenge to this explanation. The current lambda cold dark matter, lambda CDM, model attempts to account for these structures by relying on dark matter to amplify these small initial fluctuations. Even with this amplification, the existence of these structures, like the Boots void and the Sloan Great Wall, is difficult to reconcile with the Standard Model predictions. 5. Non-Gaussianities and alternative explanations. While some researchers propose that the initial fluctuations may not have been perfectly Gaussian or that other processes might have contributed to the formation of large structures, these are speculative and lack concrete empirical support. My theory, on the other hand, not only predicts the existence of these large structures but also predicts their location and shape, which directly challenges the predictions of the Big Bang and inflation models. Thus, any observation that fails to find these structures where my theory predicts would falsify my hypothesis. Critique 2. Question. Which useful, for our further understanding of the universe, predictions does your hypothesis make? Response. 1. Derivation of natural laws. My theory derives the natural laws from first principles, which means it provides a foundational understanding of how the universe operates at the most fundamental level. This includes not only the behavior of known forces like gravity and electromagnetism, but also a correct understanding of matter itself. For example, if a tokamak, a type of fusion reactor, fails to achieve stable fusion, it could be because the current model of matter and natural forces is incorrect. My theory, by providing the correct natural laws, can be used to adjust predictions for plasma behavior in a tokamak, making fusion more feasible. 2. Practical implications for asteroid impact prediction. My theory's understanding of gravity and matter means that it can be used to improve calculations for predicting asteroid impacts. If your calculations based on current gravitational models fail to predict an impact accurately, my theory offers an alternative that could prevent such errors. This has practical implications for planetary defense and could save lives. 3. Gravity control and fusion. My theory provides a correct model for gravity, which could unlock the potential for gravity control, a significant leap for technological advancement. Additionally, the theory explains fusion processes more accurately, providing the correct framework for achieving controlled fusion, which is a critical goal for sustainable energy production. 4. Critique of existing models. Unlike Guth's inflationary theory, which was never asked to produce any useful predictions, my theory not only makes predictions but does so in a way that directly challenges the empirical adequacy of current models. It corrects the flawed assumptions present in models based on Einstein's general relativity and the Big Bang theory, offering a more accurate representation of reality. 5. Predictive power with Occam's razor. The theory's predictions extend beyond just useful outcomes. They are aligned with Occam's razor. My theory simplifies the understanding of the universe by eliminating unnecessary assumptions and speculative entities, providing a streamlined and empirically testable framework that benefits our broader understanding of cosmology. Critique 3. Question. How do you address the all-good, ensche non sunt multiplicanda praeter necessitatem, Occam's razor, criticism? Response. 1. Minimalist approach to theory construction. My theory adheres strictly to Occam's razor by not introducing unnecessary entities or dimensions. The universe, according to my theory, consists solely of space, deformed space, and time, nothing more. This is in stark contrast to the Big Bang model, which requires multiple speculative entities, including the inflaton particle, a false vacuum, dark matter, dark energy, massless particles, and the Higgs mechanism, all of which complicate the theory without sufficient empirical justification. 2. Critique of inflation theory. The inflation model, central to the Big Bang, cannot stand alone. It must be evaluated within the broader context of the Big Bang theory. When doing so, it becomes clear that the model introduces complexity without empirical support. For example, the notion of the false vacuum raises the question of how the vacuum ended up in an excited state in the first place, a question the inflation model cannot answer. Moreover, the theory relies on the unobserved inflaton particle and proposes space stretching and decay of a false vacuum, which are concepts that add layers of complexity not required by my theory. 3. Comparison with Big Pop cosmogenesis. When comparing the Big Bang model, with its inflation and other speculative assumptions, to my Big Pop cosmogenesis, it is evident that my theory is more parsimonious and adheres more closely to Occam's razor. My theory avoids the need for unexplained phenomena and provides a coherent explanation based on deformed space and time alone. This makes it not only simpler but also more consistent with empirical observations. 4. Occam's razor and predictive power. By reducing the universe to the simplest possible elements, space, deformed space, and time, my theory is in perfect alignment with Occam's razor. The unnecessary complexity of Guth's model, which requires inflation to explain observations that my theory can predict without additional assumptions, highlights why Occam's razor favors my approach. In essence, Occam's razor is not just about eliminating unnecessary entities, it's about providing the simplest explanation that accounts for all observed phenomena, which my theory does more effectively than the current mainstream models. Critique 4. Question. Which, if any, of your peers have you shown your mathematics to? Astrophysicists, cosmologists, astronomers, etc. What was their opinion of both the mathematics and of the likelihood of the mathematics describing observable reality? Have you attempted to publish any of this? If so, which publications have you submitted these to, and was any of your work subsequently published? Response. 1. Challenge to the scientific community. I have openly challenged both God and the entire scientific community to criticize my theory. However, it is telling that only cognitive scientists, rather than cosmologists, astrophysicists, or physicists, have attempted to do so. This absence of critique from the relevant scientific community speaks volumes about the reluctance or inability to engage with a theory that challenges established paradigms. 2. Acknowledgement of past error. I acknowledge that I made one significant error in the past, specifically in the data analysis of the Sloan Digital Sky Survey. However, this error was corrected, and even then, it did not attract criticism from my peers. This suggests either an unwillingness or an inability to engage with my work critically, despite its potential implications for our understanding of the universe. 3. Lack of peer engagement. Despite the lack of criticism, it is curious that no serious engagement from cosmologists, astrophysicists, or physicists has occurred. My theory predicts natural laws that explain fundamental forces and matter, providing a coherent and testable framework that should attract scrutiny and debate. Yet, the silence from these fields suggests either a failure to recognize the theory's significance or an unwillingness to challenge the status quo. 4. Publication attempts. While I have not received significant engagement from the broader scientific community, the correctness and utility of my theory remain unchallenged. My theory's predictions are consistent with observations, and it stands as a more empirically grounded alternative to current models, despite the lack of formal peer review or publication in mainstream journals. 5. Rejection of mediocrity in critique. The lack of engagement from the scientific community, while disheartening, does not diminish the validity of my work. In fact, it highlights a broader issue within the scientific establishment, a reluctance to engage with theories that challenge established norms, regardless of their empirical consistency. My theory, grounded in first principles and supported by empirical predictions, remains unchallenged not because it lacks merit, but because it defies the expectations of the current scientific dogma. Critique 5. Statement. There are other observations which allow us to conclude homogeneity as a property of the universe besides inflation. Response. 1. Homogeneity acknowledged but not an inflationary result. Nobody is rejecting the idea that the universe is homogeneous. However, it is crucial to recognize that there are no observations that specifically support inflation. Inflation was introduced to explain the uniformity observed in the cosmic microwave background, CMB, but it has failed to account for more recent astronomical observations, particularly regarding large-scale structures. These observations contradict the notion of a perfectly homogeneous universe because they focus solely on luminous mass and ignore the total mass, including gas. This focus leads to flawed conclusions. 2. Flaws in the Big Bang and inflation models. The Big Bang model and the accompanying inflation theory do not predict the existence of large-scale structures like voids and filaments. These structures are too large to be reconciled with the nearly Gaussian initial fluctuations predicted by inflation. My theory, in contrast, not only predicts these structures but also provides detailed predictions about their location and shape, which the standard models fail to do. 3. Misinterpretation of observations. The visible universe, when considering luminous mass, appears inhomogeneous, with structures billions of light-years across and vast voids. My model predicts not only these inhomogeneities but also explains their formation within a homogeneous framework that includes gas clouds and total mass distribution. The universe was homogeneous at the time of the CMB, and there is no reason for the mass distribution to become inhomogeneous, despite variations in luminous mass. The observations of inhomogeneity are due to differences in luminous mass, not total mass, which aligns with my theory's predictions. 4. Inadequacy of current models. The current cosmological models, including the Big Bang and inflation, cannot adequately explain the existence of these large structures or reconcile them with a homogeneous universe. In contrast, my theory accounts for these structures within a more coherent and empirically supported framework, which further challenges the assumptions underlying inflation. 5. Ultimate refutation. The ultimate refutation of the inflation model lies in its failure to account for these observations and its reliance on speculative entities like the inflaton particle. In contrast, my theory provides a simpler, more accurate explanation that does not require the unsupported assumptions of the Big Bang model. Thus, the first paragraph supporting Einstein and Guth is effectively shot down, as my theory better aligns with observed reality and the principles of Occam's razor. Critique 6. Statement: it's easier to learn about the Nobel Prize than to study astrophysics. Response: 1. Irrelevance of awards. You emphasize the Nobel Prize as though it were the ultimate measure of a theory's validity, but it's not the final arbiter of scientific truth. The fact that the Nobel Prize is awarded only for discoveries made in the previous year has led to many oversights and omissions. This temporal limitation means that many significant discoveries are not recognized in time, leading to the false elevation of less impactful work. 2. Critique of Guth's recognition. Dr. Alan Guth's work on inflation, for instance, despite being recognized with the Kavli Prize, does not align with observations. When Guth first wrote his inflationary theory, it was decades before any observations were made that supposedly validated his hypothesis. Even now, the theory does not fit the facts as well as my theory does. The recognition Guth received does not change the fact that his predictions were rejected by the existence of large structures and that no observations other than the cosmic microwave background, CMB, exist to support his model. It is irrelevant whether Guth received a Nobel Prize, a Kavli Prize, or a hug from his mother. What matters is the empirical consistency of his theory, which is lacking. 3. Inflation versus my theory. Guth's theory is not useful for anything and cannot be proven true. In contrast, my theory offers a simpler model that produces a homogeneous universe without the need for dark matter, dark energy, inflation particles, which have never been observed, space stretching, or false vacuum decay. The Big Bang model, which includes inflation, is riddled with unsupported assumptions, while my Big Pop cosmogenesis avoids these complexities. When comparing the two, it becomes clear that my theory is more consistent with empirical observations and adheres more closely to Occam's razor. 4. Rejection of smeared critique. You also attempt to undermine my work by suggesting that my lack of awareness regarding Guth's Nobel Prize situation somehow discredits my theory. This is an invalid argument. Moreover, you admit to being a cognitive scientist and not a physicist, which inherently disqualifies you from making informed judgments about the physical reasoning required to evaluate my theory. Your critique is thus based on ignorance rather than scientific merit, and your attempts to smear my work by proxy are baseless. 5. Final rebuttal. Awards and recognition are not reliable measures of a theory's correctness. What matters are empirical observations and the consistency of a theory with those observations. My theory passes this test. Guth's does not. Your focus on awards rather than the science itself reflects a misunderstanding of what truly matters in scientific discourse, the evidence.